So in later math classes, you might be reading and it might say something like, by the division algorithm, or using the division algorithm. And this division algorithm really is essentially just describing what's happening with division, which you've known since grade school. What happens with division? We are applying it to polynomials. So notice there's all those function notations in there. There's basically 4 functions that they're describing, right? F of x, d of x, and at the end, q of x and r of x. And then you see them in the statement. The thing that I think is always kind of funny about the division algorithm is the way it's written here, there's really no division. I'm going to go to that example that I did over here on the sideboard already, where I just took 2 numbers, 17 divided by 5. And back when you learned about division, you should have talked about what some of these things were called. So the one that people usually are least likely to remember is the one underneath the division sign. This is called your dividend. Does anybody remember what the thing you divide by is called? The divisor, so that would be our 5. And then the answer to a division problem is your quotient. And of course, on this one, we also have a remainder. So if you recognize that those are the parts of the division problem, notice in my division algorithm where I'm describing all my polynomials, there's a d of x, a q of x, and an r of x. So those things are describing some of the parts. Like this r of x is really just your remainder polynomial. Q of x is your quotient polynomial. And we have 2 words that start with D, divisor and dividend. The d of x in the division algorithm is your divisor. Yep, f of x will be your dividend. So, like how can I decide which one is which? When I read that first sentence of the division algorithm, if f of x and d of x are polynomials such that d of x does not equal 0, well, why would I say that d of x could not equal 0? Because I can't divide by 0. So that's automatically my divisor. I'm taking some function f of x, and I'm dividing by another function as long as it's not equal to 0. Okay? And it also says something here. The degree of d of x is less than or equal to the degree of f of x. So that should make sense to you. Like, I'm actually going to flip back to Christopher's work on the warm-up. If we switch these 2 around, it would be hard to divide a linear function by a cubic function, right? So we're just saying that the one inside has to have equal degree or greater degree than the divisor on the outside, okay, so that we can actually do division. And then if those are 2 polynomials, there are some unique functions that happen to be your q of x and your r of x, and this thing will hold true. F of x is equal to q of x, or d of x times q of x plus r of x. So I'm going to look up at my example where I did 17 divided by 5, and do you agree that the dividend is equal to the divisor times the quotient plus the remainder? Checks out. Okay. If we look at our warm-up problem, so because that has actual polynomials with many terms, if we look back at our warm-up problem, we're saying that x cubed minus 2x plus 5, that polynomial f of x, is equal to the divisor, x plus 3, times the quotient, x squared minus 3x plus 7, and then plus your remainder, which just happens to be a minus 16. So if we took the time to distribute and combine like terms and then subtract 16, we will get that 3-term polynomial x cubed minus 2x plus 5. So that's really all that the division algorithm is saying, like this is how division works. And we all agree to that. Okay. But then we can use division and the division algorithm to find out interesting things about our polynomials. So here's the 2 most helpful theorems for today. Okay. We're going to start with the remainder theorem, and then we're going to do the factor theorem. So make sure you get these 2 in your notes, remainder theorem and factor theorem. If a polynomial f of x is divided by x minus k, then the remainder is f of k. Well, that would be what we call direct substitution, but we're going to do it through division. So we're doing remainders. Okay, there's a couple of important things to note about the remainder theorem. The first statement tells you for which cases you're allowed to use this. Polynomials divided by something that looks like x minus k. So you're often going to hear me refer to this as a linear factor. Okay, so we can use this remainder theorem when we're dividing by linear factors. Well, what happens in those cases is that second statement. Then the remainder is f of k. What does that mean? The remainder in your division is the y for your given x. So it is like when we just sub in x's and we work out to get y, but we're not going to use direct substitution, we're going to use division. So do you see how we're taking 2 polynomials divided by each other? Okay, let's do that. We'd probably choose to do this one by synthetic, right? Because it's a linear factor. That would be quickest. So I have no missing terms to worry about. I'm going to drop in my coefficients, 3, -4, -41, and 35. And if we're dividing by the linear factor x minus 4, what do I put on the outside of synthetic? A positive 4. Okay, and then remember there's basically 2 things you do in synthetic. Add, multiply. Good luck.
Thank you.
So we always add down first, so we're going to drop our 3. Multiply 3 times 4 is 12. Add down to get 8. Multiply 8 times 4 is 32. Kiara, I'm wondering, does this look like anything you've ever done before? Okay, good. Okay, add down to get -9. Multiply, get -36, and then we get -1. Now, we can do a lot with this synthetic. We could do what you guys did for me on the warm-up, which is write the answer, the quotient plus the remainder over the divisor. We could do like what we did on the division algorithm. We could say this whole cubic polynomial is x minus 4 times 3x squared plus 8x minus 9, and then -1. Or we can use what we know about the remainder theorem, which is to say that the remainder, which is -1, is the y value when x is 4. So basically in function notation, that's saying f of 4 is -1. Or it's giving you an ordered pair, an x and a y. So you also know that 4, -1 is a point on your graph. If you ever needed to like generate a bunch of points for a polynomial, you could just use basically synthetic division and put in different linear values and work it out, and you would have a whole bunch of y values that you could then plot. So we would go, what, right 4 and down 1, nothing really interesting about that point. But what would be really interesting is if my remainder came out to be what value? 0, because then what special kind of point would I have? A0, which looks like an x-intercept on our graph, right? So that's where we're going with this. The remainder theorem gives us our y values for the function. But wouldn't that be wonderful if we got 0? Because then we know it's an x-intercept, it's a solution to the polynomial. So we're headed to the factor theorem next. Factor theorem is a continuation of your remainder theorem. Factor theorem says this: a polynomial has a factor of x minus k if and only if f of k is 0. Do you remember the IFFs, if and only ifs? Those are in geometry, you call them biconditional statements because you can say them either way, forwards or backwards. If your polynomial has a factor x minus k, then f of k is 0. Or if f of k is 0, then it's a factor. You know, as I'm using remainder theorem throughout chapter 2, this is in my own words what I think about. If the remainder is 0, then it's a factor. So like in my own words, what's the benefit of the remainder theorem, or sorry, the factor theorem? I can tell if something is a factor or not. And you might be thinking ahead to different things that you've done before with polynomials in Algebra 2 or Algebra 3. We are interested in the factors because we want to find the zeros, the x-intercepts. So this is one way that we can factor. So my question to you is x plus 3 a factor of this polynomial? To check it, just set up division. If it is a factor, then the remainder will be 0. Now, do be careful on this one. You're missing the x squared again. So you got to put in that 0 placeholder. That will really mess you up if you don't have that. You won't get a 0. And then if we're checking x plus 3, we're going to put a negative 3. Fingers crossed, we're hoping for a factor. I always put smiley faces in mine. They make me happy. I love zeros. It's an x-intercept. It's a solution. Feels good. I should be smiling. So my 0 smiles. Isn't that awesome? But if you get a 0, it means it is a factor, right? So yes. It's a factor. Can you then write the complete factorization of the polynomial? That's a really wordy way to say factor it completely. Yeah. So in this original form, x cubed minus 19x plus minus 30, those are all terms. They're no factors. But we just checked and we found out x plus 3 is a factor, right? So one of my factors is x plus 3. The other factor is this quotient that I got right here, no remainder. So that's going to be x squared minus 3x minus 10. Is that the complete factorization? No, because I can still factor x squared minus 3x minus 10. So that's x plus 3 times x minus 5 times x plus 2. this is completely factored. That's what a complete factorization is. One thing that happens a lot for students when I ask for like the complete factorization is a lot of people only factor the quotient and they forget to put back the original factor that they checked. So one way for you to check if you have the complete factorization is, like if your original function was cubic, how many factors will you need? 3 linear factors to make a cubic polynomial. If I forgot my original factor, I know that I'm only writing a quadratic, not the original f of x. So I add that one back in. Okay. Any questions or clarifications you would like me to make for factor theorem or remainder theorem? Okay, to sum it all up, you don't necessarily have to write this down, but you can if you want. These are things that, why are we saying polynomial division? These are things we know from remainders. We can know the value of the function at x equals k. If the remainder happens to equal 0, we know that it's a factor, and we know that we have an x-intercept or a 0. So think about like page 133 and 134 when you're trying to graph polynomials. Don't we want to know the zeros so we can put them on the graph? Okay, so this would be really handy.